Oftentimes, the classes of mathematical objects which are most central turn out to be invariant under a variety of natural transformations. Or in other words, they are preserved under a number of different operations. And sure enough, it turns out that positive semi-definite kernels exhibit this sort of characteristic. So besides being mathematically appealing, this type of behavior, that being preserved under different operations, is very handy for constructing new objects of whatever the sort that you're interested in. So here we start out with a positive semi-definite kernel, and we do something to it, and we get another positive semi-definite kernel. So this video is going to be a toolkit of sorts for how to do this, how to construct positive semi-definite kernels. Of course, we saw how to construct them using inner products, and that's maybe the hammer in the toolkit, but there's a bunch of other tools that we can use as well. So we have this theorem, and we're going to list a bunch of these operations. So if k, k1, and k2, we're going to just start out with a handful of kernels with different names, are, let's say, real or complex valued positive semi-definite kernels. Maybe I'll remind you of the definition of the distinction between those in a second. On some arbitrary set S, then the following are also real or complex, respectively, positive semi-definite kernels. So maybe just to remind you briefly, a real positive semi-definite kernel, that's the one we've been mostly using, that has the property that it's symmetric. So for any finite number of points, the matrix that you get, maybe C, is symmetric, so it's equal to its transpose. And for any vector u, we have u transpose cu non-negative. And just to remind you what a complex positive semi-definite kernel was, in that case, the matrix that we got C was Hermitian, so it was equal to its conjugate transpose. And we had that u conjugate transpose cu was non-negative for any complex valued vector u. So in each of these statements, if these are real, then what you end up with is a real positive semi-definite kernel. Maybe let me write that line down here so that's clear. And if you start out with complex kernels, then you end up with complex kernels, but you can't mix and match in this theorem. Okay, so the first one, finally we get to the first one. The first one is the simplest, maybe, in some sense, if we just multiply by a constant. So we're going to take k here, multiply it by some non-negative constant, and this is a real positive semi-definite kernel if k was real, and complex if k was complex. Okay, I'll stop saying that about real and complex now. Switch to a new color. So multiplying by constant, and also if we add them, k1 xy plus k2 xy. This is also a positive semi-definite kernel. And if we multiply them, k1 xy multiplied by k2 xy, this also has the same property. And maybe I'll mention at this point, I'm not going to give the proof of all of these because most of them are very simple. Most of the proofs are just, you just check these properties, and it's trivial to check them in most cases. But in case number 3, it is actually a bit subtle. So I am going to give you the proof in the next video of number 3. Okay, so number 4. Number 4 says that for any polynomial p, if we evaluate that polynomial at the value of the kernel k, and that polynomial has non-negative coefficients, then we get a new kernel non-negative coefficients. That's important. So in other words, if p was like 1 plus x squared, then you would have 1 plus kxy squared. 5. Let's make some space. 5 says that, so this is sort of a generalization of 4. If we take the exponential, if we take e to the kernel, not really a generalization, I guess, but it's you can use 4 to prove 5. This is also a kernel, positive semi-definite kernel. And so maybe I'll make a remark here about how to prove 4. 4 you just would use 1, 2, and 3, right? Because you could construct any such polynomial with non-negative coefficients by some combination of these operations. And then for 5, you would prove that by using, using 4, you would write down the, this is e has a e, e to the x has an infinite series representation, and you could write that as the limit of a sequence of polynomials, and each of those polynomials would have non-negative coefficients. So you could take 4 and then take the limit of a bunch of non-negative numbers, and then you would show that 5 is also non-negative, or it gives you a non-negative thing. Okay, 6, and a bright neon pink. That's nice. So for 6, we're going to have some function f, and we'll take f of x times kxy times f of y. And for this, I'm going to put the complex conjugate of f of y to hand. In the real case, of course, well, maybe I should say what f is first. And this is for any f from s to, well, it would be r in the real case, and it would be any f from s to the complex numbers in the complex case. In other words, if k is a real positive semi-definite kernel, and we take a real function f, then this defines a new positive semi-definite kernel, real valued. And on the other hand, if k is a complex positive semi-definite kernel, and we take any complex function f, then this defines a complex valued positive semi-definite kernel. And of course, the complex conjugate, it doesn't play any role in the real case, because the complex conjugate of a real number is equal to itself. And 7 says that if we precompose k with some map phi, so in other words, we take k of phi of, or rather psi, k of psi of x, psi of y, then this is a kernel for any map psi from, so far all our x's have been in x, or rather in s. All of our x's and y's, all the arguments to this kernel have been in s. And now we're going to, a slight change of notation maybe, the x's and the y's are going to be in some s prime, and psi will map us into s. So k is still a kernel on s, as we originally defined it to be. And this was for all. Okay, so that's all of our little toolkit, our little library of operations that preserve kernels, positive semi-definite kernels. And I would encourage you to prove these if you're interested in understanding these guys. Proving these is a good exercise in knowing how to work with these kernels and prove things about them. So I am going to give you the proof of 3 in the next video. That's the only one that's really kind of tricky, I think, at least. It's tricky. And but the rest should all be pretty straightforward to prove.